Okay, so here's where we were last time. We had just gotten to defining double integrals. We previously defined iterated integrals, and that helped us solve one question. It helped us solve, for example, the question of volume under a graph of a function of two variables. But we found that trying to take a seemingly analogous approach to answering a question about mass, just as a first, for example, as a second possible application, and it fails. It doesn't make any sense. The argument doesn't hold water, as it were. So what we're going to do then is define this new thing called a double integral. And in order to define a double integral, I had to remind y'all what the definition is of a single variable integral. A lot of students misunderstand this and think that Riemann sums are an outdated computational tool that was supplanted by the fundamental theorem of calculus. I mean, after all, why would you mess with the Riemann sum when you can just use the fundamental theorem, much more powerful, right? Well, not only does that not work on a chronological level, Riemann was not born yet when Newton came up with the fundamental theorem. It also is just not true in terms of applications. It is very important that we understand Riemann sums in order to be able to make applications. After all, that's the argument that we can make in terms of, if somebody asks us to compute a mass of a one-dimensional rod, thinking back to single variable calculus, just a one-dimensional rod, right? You chop it up into little pieces. On each piece, you can talk about mass per unit length times the length, and then you add that up. And notice that's got nothing to do with area. Right? It just doesn't. Mass per unit length is independent of area. They're just completely different things. So there's no natural immediate argument connecting mass to area. There is, however, an immediate connection that you can make between mass and a Riemann sum, because as this formula here directly says, you chop it up into little pieces. On each little piece, mass per unit length times length gives you little pieces of mass. And if you add up all the little pieces of mass, you get the whole as the sum of the parts. And there you go. That's sort of an immediate use of this formula to compute mass. So it's very important that integrals be defined accordingly, so that when we use the fundamental theorem of calculus to compute an integral, that integral can actually represent something like, some sort of application, mass, population, probability, what have you, any number of different applications. Okay, I'm going to try to restrain myself from spending too much time talking about this. I can go on forever about this particular topic. If you want to hear more about this topic, why Riemann sums are important, how students very often misunderstand this, I recorded a short recording on this topic. It's about 30 minutes. It's everything that I wish all my students understood about single variable integrals. It's on my YouTube channel, miscellaneous topics playlist. And I think it's called What is an Integral? And I've got a few other little soapbox speeches in that same recording also relating to integrals. Okay, enough of that. Point being, single variable integral, Riemann sum. What I like to call chop it up, add it up. You chop up your domain into little pieces, you add up the answers to those easy questions to get the whole. Okay. All right, so we're going to try to do kind of morally the same thing now in a two-dimensional setting. Sometimes, for example, mass is not distributed across an interval. Sometimes mass is distributed across an area. Right? So instead of, for example, asking for the mass of a one-dimensional rod, maybe you're interested in computing the mass of a sheet. A two-dimensional sheet of metal. Or, something, whatever. Or maybe you want to compute the population of Wyoming or Colorado. Take your pick. Right? Rectangles only for the moment. We'll get to non-rectangles a little bit later. Whatever it may be, if we decide that we want to chop up a rectangle, notice we kind of have to chop in two different directions. If you just chop up like this, you don't get little teeny tiny little small little pieces. You get long skinny pieces. So you have to chop up in both directions we go. Chop it up in both directions. Then you get actual little bitty pieces of area. Like that. All right. Let's see here if I can get all this to erase. How we doing? Is everybody with me so far? A lot of details we need to talk about. Okay. So the big idea, and we'll get to the details in just a moment. The big picture idea is if I'm computing the mass of this piece of sheet metal, whatever it is, on each little piece, I have a relatively easy question. On this little teeny tiny little piece, the density, the mass per unit area on this little piece, because it's so small, is approximately constant. And so I can just say mass per unit area times area. Notice it fits. It's not one of these mismatches where I'm multiplying mass per unit area times length. Mismatch, right? Here, I would multiply mass per unit area times that area. And you can see that's exactly what this, for example, might be. Mass per unit area could be my integrand. And then area, size, right? Being a little rectangle, it's going to have a width and a height. We'll talk about those details in just a moment. But mass per unit area times area. And then if I want to add up over the entire rectangle, then I just add up the answers that I get on all of those individual little pieces. Okay, big picture, details aside, everybody kind of see roughly how this is pretty much the same as in single variable calculus. In single variable calculus, it's mass per unit length times length that helps me compute what I'm interested in on a sub-interval. Here, sub-rectangle. Okay. All right. Okay, so let's talk about some details. I need to be able to keep track of where I am along the x-axis. I'm going to need to know, for example, the coordinates of some point in each one of these sub-rectangles. These points down here will be, those coordinates for different rectangles. Notice, effectively, we are just like in single variable calculus, taking the interval from A to B and chopping it into n pieces. So, exactly the same results there. B minus A over N, A plus I delta X. Presumably, hopefully y'all remember those details from Calc 1. Calc 1 or Calc 2, depending. So now we just have an analogous thing happening over here. We have this interval from C to D. Different letters, sure, right? But still it's an interval that I'm chopping up to N little pieces. And so I'm going to get a delta Y formula. It looks exactly the same, adapted appropriately, of course, and a Y sub J formula that, highly analogous, adapted appropriately, of course. Notice that I'm using J as my index on the Y-axis. I've already used I as a tool for keeping track of where I am horizontally. So I need a different index. I'm going to use J, keeping track of these subscripts where I am, in other words, along the vertical axis. Okay. So, there's those details. So we're good at this point. This is now a well-defined thing. This will compute the mass of that sheet. It'll compute the population of Wyoming. It'll compute whatever it is that you're adding up over a rectangle, whatever it may be. This expression will add it up for you. So being as it is the answer to so many of these questions, and we're going to see a bunch of examples over the next several lectures, we're going to give this a name. This is called a double integral. This expression right here. It's a Riemann sum. It's what you might call a two-index Riemann sum because there's both I and J varying across all these different values. And in addition to name, we're going to give it a notation. And that's this notation over here. Notice that this is really just kind of a stand-in for that, if you will. And this is kind of just a stand-in for that. I emphasize the thing that we're actually doing. The actual mathematical object here is this Riemann sum. All this stuff on the left is shorthand, right? It's just a convenient way, less pencil strokes, to represent what we're actually doing. Okay. I should mention there's some things in the book that we're not going to worry about. So irregular partitions and arbitrary test points. This is just formality stuff that is extremely important if you're doing real analysis, if you're doing more sophisticated kinds of math, if you need to prove various theorems that we're going to just kind of assume and use in this class, then this is a big deal, very important, and frankly very beautiful mathematics. It is beyond what would be reasonable for Math 219, so y'all are not responsible for it. I'm morally certain I have noted such on the content syllabus, but I just wanted to point out to you when you're reading that part of the book. I mean, take a glance at it if you're curious, but you're not responsible for it. Okay, alrighty, so quick example. Volume under a graph. Now we already know the answer to this question. We already know how to compute volume under a graph. Iterated integrals. Crush that problem. It's great. But iterated integrals crush only that problem, right? So let's try to see, let's try to get more use with this new tool that we have, the double integral tool. And here we go. Let's take our entire volume, and I'm going to view that as being something that's happening on this rectangle. Right, I have volume sitting over that entire rectangle. I'm going to focus my attention on just one sub-rectangle at a time. The volume sitting over each one of these sub-rectangles is a much easier question. It's basically a rectangular little tall, skinny, I like to think of it as a French fry. Very tall, very skinny in both horizontal directions, and that has a volume that's pretty easy to write down. It's the height times the area of the base. Nothing to it. All right, the height's approximately constant on this little teeny tiny little piece. So that error from the non-constantness of the height is going to go away in the limit. Nothing to worry about. And height, value of the function. Delta x, delta y are the length and the width. There's our volume. And then you notice that adding up over the entire domain, taking a limit, of course, deal with those pesky round-off errors, makes this expression turn exactly into a Riemann sum, and therefore exactly into a double integral. Right. How we doing? Everybody all right? Okay. Alrighty. Now, this does allow us a pretty neat observation that we can make here, which is that, let's see, we previously computed volume as iterated integrals. We did that last time. Now, we've just gotten through showing that we can also compute volume with a double integral. So, both of these things down here are ways of computing the exact same thing, namely volume. And that means that these things here, bad color choice. Let's see here, I'll use red. These two things here are equal to each other. So double integrals can be computed with iterated integrals. Everybody all right? Okay, so now I want to pause and take stock of, we've got various different constructions, we've got various different connections between them. I want to bring it all together, here's a little roadmap, as it were, of concepts that we've talked about. The very first thing that we did is we said, hey, let's compute volume. We did so by inadvertently creating this construction called an iterated integral, and we found that we can compute iterated integrals with the fundamental theorem of calculus. And that's nice and all. I mean, this is cool, I suppose. But we also found that this is a very limited thing, because if you try to make a connection, we talked about the details of this, if you try to say, I want to compute mass, I'm going to view mass as being a volume, but it's not. So you can't really do that. If you instead say, okay, well, I want to compute mass by using an iterated integral approach? Well, we saw that there was this mismatch of, we were multiplying mass per unit area times length, and that's not a thing. We can't make an interpretation of that. So we're kind of dead in the water here. Or we were dead in the water. We got all these applications, and I can't connect any of them to this iterated integral portion of the diagram. So, not good. This is where we found ourselves coming up with this new idea of a double integral. Brand new idea, right? Fundamentally different, analogous, but very structurally different from single variable integrals. Much more so than iterated integrals. If you think about it, iterated integrals is just creative use of single variable integrals. This is literally a single variable integral of a single variable integral. Hardly even new. Barely new. Right? Double integrals, completely new construction. And we made the observation that double integrals could compute volume, and then seconds ago I pointed out that, well, if we double integrals compute volume, and if volumes are also computed by iterated integrals, then we have this connection there between double integrals and iterated integrals. Okay, so that's what we've done so far. Oh, it's a lot of stuff. Is everybody happy? Is everybody with me? Okay. So, now that we have all this noted, we've got all the connections, all the allowable connections noted, all of the not allowable, not reasonable connections eliminated. We played the how do you get there from here game, and if I have an application problem and I want to compute an answer, how am I going to proceed? What is the path of my argument? Well, obviously, I'm going to first write the answer to my question as a double integral. Step 1, got to write the answer to your question as a double integral. Step 2, I'm going to rewrite my double integral as an iterated integral. Step 3, I'm going to compute my iterated integral with the fundamental theorem of calculus to get my final answer. Does that all make sense? 3-step process. Don't forget, the point to this course, right, is not the answer. Right? Answers are only part of the story. What we're interested in this course, where points come from on exams is not the answer, it's the argument. This is where points come from. Right? So make sure to give me the argument. In particular, as applies to this sort of situation, if you are solving an application, what I want to see is all 3 steps. I'm going to show you an explicit example momentarily. I want to see the double integral. I want to see that rewritten as an iterated integral, and I want to see that then directly computed plug and chug. Okay, let's do an example. Alrighty, we're going to compute the mass on a rectangular sheet where mass per unit area is a given known function. By the way, the work that I've got shown here is much more than I expect you to actually write down. I've written it out fully expanded just to be as explicit as possible for sort of, talking, teaching purposes. On an exam, you'll write something much more streamlined than this, and I'll be explicit about that as soon as we're done with the expanded discussion. But anyway, here we go. Let's talk about step 1. How do I turn my application into a Riemann sum, aka a double integral? Well, mass is an accumulating quantity. The whole is the sum of the parts. That's just the nature of mass, right? I think that's intuitively satisfying. I've never taken a lump of mass and cut it in half, and somehow the mass of the pieces don't add up to the same amount as the mass of the whole. That'd be disturbing, right? Mass is the sum of the parts. In each piece, mass is mass per unit area times area. Yeah, sure. That's the definition of mass per unit area. That's what we mean by mass per unit area. And then you notice that this is the very definition of a double integral. This is explicitly a Riemann sum, and so I can write that then as a double integral. Okay, so this is step 1. That's this right here. Everybody good? Step 2. We're going to turn our double integral into an iterated integral. Well, that's not that much to write down there, but turning a double integral into an iterated integral, well, here's the iterated integral. I already know what my bounds are. Let's see here. So the fact that the rectangle, the x values on the rectangle are from a to b, that tells me my x bounds are a and b. And the fact that my y bounds, the range of values for y is c to d, that tells me my y bounds are c to d. So boom, there's that. Everybody good? All right, so again, step 2, let's see, let me clean up my mess here. Step 2 is that. And then step 3, crank it out with the fundamental theorem. We've already done several of those. I'm going to leave that as something for y'all to do for each individual question as we see them. There's nothing to be done here because we don't have an integrand actually given to us, but it's just a matter of working from the inside out. Right? You got to do your inside integral first, outside integral after that, and an answer will result. Okay, so these 3 strategic steps look like this, fully expanded. But now let me show you in practice. Actually, in practice, what are you actually going to write down on an exam? You're going to say mass is a double integral of density, which is this iterated integral, and then you're going to compute with the fundamental theorem. So it's very streamlined. Very, very, it's not like I'm asking you to write out, again, a bunch of stuff like I did here. Really, the main thing that I want to see, you couldn't possibly do this part without writing down the iterated integral. The iterated integral, you can't even proceed without writing the iterated integral. The main thing that I want to make sure students don't do is this right here, right? Please do not just immediately declare the answer to your application as being an iterated integral. Because after all, that's this move. And we've agreed that doesn't make sense. It's the pieces don't fit together. As an argument, it doesn't hold water. Right? It's just not appropriate. So you can't do that. So the upshot is, all you really have to do is just make sure to write down the double integral before you write down the iterated integral that you're then going to proceed with. Very, very little extra that I'm asking. Just make sure to write down the double integral as this intermediate step before you get down to business. Does everybody see what I'm requiring? Questions? Feel free. We're doing good on time here. Alrighty. So, I want to say a real quick thing about notation. Not that you necessarily would write this out every time. I don't. Most people don't. But if you do find yourself developing a Riemann sum as you work your way up to a double integral, notice this sort of alternative notation down here. I find this very convenient. It's very natural. If you look at the notation for, here's a double integral, a Riemann sum, and then here's effectively a kind of a double integral. And notice, this notation here is pretty suggestive. It's pretty clear what we mean by that. And then likewise, you can think of this as a shorthand for that part right there. And if you're going to use these two integral symbols, or you might say the double integral symbol, as a shorthand for the limit and the summation, well then why not do it over here too? It's just handy. And there's a little fewer pen strokes, easier to write. arguably a little sloppy. I mean, technically I haven't defined this expression right here, double integral dm. I haven't really written that down as a formal thing, but you know what I mean. This is just shorthand for that, which is part of my development. So be aware of this. I encourage doing things this way. It's more compact, it's more convenient, it's more common. So feel free, and again, feel encouraged. Okay, all right, let me show you where that is actually pretty useful. Sometimes you have to do a little bit more work in developing your Riemann sum. This is a kind of an engineering example. Let's suppose you're building a wall. So the vertical axis is up here. This is not a horizontal XY plane. Y is up. And let's suppose that your wall, for whatever reason, oh, by the way, it's got a width of 10 and it's got a height of 6. Just making these numbers up. And let's suppose that it's made out of, stone or brick or something heavy, where you're actually concerned about the effort, the work of having to pick up these heavy things and lift them up off the ground up to where they're going to be in the wall, and that's going to add up to a lot of work if these are heavy stones or what have you. And so, how much work does it take? Ignoring, of course, that there's a lot of other kinds of work involved, right? But just the mere, working against gravity with the stones, how much total work does it take to build this wall? So I'm going to use, you're going to notice here, this kind of integral shorthand notation as I develop my Riemann sum. And it's going to be very convenient shorthand. First, I write this down. This is my shorthand for saying that work is an accumulating quantity. The whole is the sum of the parts. Chop it up, add it up. However you want to say it. The total amount of work is the sum of the amount of work that it takes me to do each individual brick or stone or what have you. Is that cool? Next, how much work does it take to lift that one stone? It's going to have a certain weight to it, differential amount of weight, right? As we take the limit, the pieces get smaller and smaller, so the weight of those differential pieces gets smaller and smaller. And I'm going to have to lift it up a certain height, namely whatever y is. However high it is off the ground, that's the distance I'm going to have to lift it from its starting point at 0 on the ground. So altogether, work equals force times distance. And again, this by itself, in the absence of a context, arguably doesn't mean anything. But it's a shorthand, and I think it's clear, what's suggested here. That I'm adding up a bunch of pieces. Each piece has a differential amount of weight and being lifted a certain height, and I'm adding them all up. It's shorthand for a Riemann sum. Next, weight is density times size. Again, appropriate to this context, I'm thinking of this density up here as telling me weight. How many pounds does the stone material weigh per unit area? Got this function up here, and weight per unit area times area gives me weight. And now, having done these 3 steps, I've got myself an actual double integral. And so this is something that I can proceed with. So I've got kind of there's my phase 1 of the argument. Phase 2, turning the double integral into an iterated integral, is not that big of a deal. It's just kind of a matter of recopying, plugging some formulas in. And then phase 3, the actual plug and chug computation, is what follows from that. How we doing? Everybody okay? Feel free to ask a question if you got one. Okay. All right. Okay, so now next question. We've extended things quite a bit from iterated integrals. Iterated integrals were really good for only one thing. Iterated integrals allowed us to compute. It was very limited. much more broadly, we can now compute the answer to a huge number of applications. Anything that accumulates, anything that you can chop it up into little pieces and the whole of some of the parts. Double integrals allow us to compute mass, work, population, you name it. Okay. Now we're going to extend it even more. What if the quantity in question is distributed over something that's not a rectangle? Right? Everything we've done so far, rectangular domain. Only defined on a rectangle. So, if I have a non-rectangular domain, such as this lumpy thing right here, and if I ask similar questions, such as, well, I want to compute the amount of, I want to compute the amount of volume in here, sitting under a graph. Just like we did over a rectangle, but this now over not a rectangle. How would I compute this volume? And I'm going to point out that we can pretty much proceed exactly like we did before. Basically, nothing goes wrong. The total volume I can slice up into little pieces, and the whole is the sum of the parts, independent of what the shape of the footprint is. Right? It doesn't matter what kind of bread you buy. The total amount of bread in the loaf is the same as the sum of the amounts of bread in each slice of bread. That's, same exact point. Each little slice of bread is a cross-sectional area times the thickness. Same. That cross-sectional area, let's see here, let's see the cross-sectional area here. I can compute as an integral again because, again, it is the area under a curve. Everything's the same. So, you want to do a double integral over a not rectangle? Yeah, cool, go ahead. It's fine, not a problem. Except for one thing. There's a little micro detail that does change. It's just a micro little logistical point. But if you look at these inside bounds, and I'm going to zoom so we can see a little bit better here. This inside bound right here, for example, a of y. Notice I'm claiming that it depends on y. Depends on where I am in my outside slicing process. And, well, yeah, of course it is. If you think about it, because that bound, the x-coordinate, why does that depend on the y value? Well, because this point that defines the first part of my integral, as I'm going in the x direction to compute that cross-sectional area, just like before. That point that defines my starting place is going to be on this curve. And on that curve, x depends on y. You can geometrically see it. Like if y were to move slightly over to the left, right, if this were to go over to there, well, then this point would not only move to the left, it would also move somewhat in the x direction, because this purple curve is not a straight line. So the way that let's see, I'll say it like this. The value of A depends on Y, so it's a function of Y. Does everybody see that? Likewise for the upper bound, of course. Okay. All right, next thing I want to point out. The argument that we just made for why it is that this bound and these inside bounds, that they depend on the outside variable. The entire argument that we made there took place in the XY plane. Now, there is a vertical axis here, right? But the height's got nothing to do with this part of the argument. This bound only depends on where this sort of corner is, which is always in the XY plane. Said differently, these bounds only depend on the domain. The value of the integrand is irrelevant, right? So you don't even have to draw this three-dimensional picture, which is good news, because three-dimensional pictures are hard to draw, right? And I'm sure you all have noticed that. This is a skill. This takes effort and time. Even if you're good at it, it's inconvenient. So, great news. We do not have to draw those three-dimensional pictures. We can instead draw just... we can draw just the XY plane, on which we only need to note just the curve that relates the value of y to the resulting value of x, right? And this yellow part of the picture down here, you can just look at that directly. Much easier picture. No 3D. No perspective drawing of your shape, which is always a little tricky to do. And so just look at your domain alone. Everybody buy it? Okay. So all together then, I'll point out that the bounds that we're interested in between other things involved, between them and the y coordinate, defines this point, which of course is on this curve. That curve has an equation. And so if you want to find the bound, notice this bound, right, what it is it's the x-coordinate of a point on this curve with that equation. So said differently, if you want to find this bound, you literally just solve for x in this case. Just solve for x in the equation for the curve that contains the point that defines the bound you're looking for in the first place. Solve for x, and that tells you the formula for your bound. That make sense? So when y'all are doing non-rectangular domains, this is the process that I want you to do. The thing that you're looking for is going to be defined by a point, which is going to be on a curve that you can recognize from your picture, which will have then some sort of an equation, right? And then you're just literally going to solve for x in that equation to get your bound. Let's see an example. Okay. All right. So let's take this triangle right here with certain vertices given. There it is. How are we going to do this double integral on that triangle? Now, before we get into the weeds on this, I want to go back to the diagram where we, our sort of strategic diagram here, and point out that I'm starting with the double integral. Our goal is to figure out how to write this as an iterated integral. That's it. So in this question, I'm not worrying about where the double integral came from. I'm also not going to spend time in this example on talking about how would I go about getting an answer. How would I plug and chug compute the iterated integral? Because you already know how to do the fundamental theorem of calculus. We've done several examples of computing iterated integrals with the fundamental theorem of calculus. Let's plug and chug. And where the application comes from, where the double integral comes from, what application we're talking about. We've seen some of those as well. This is the new part. For non-rectangular domains, turning a double integral into an iterated integral is our new thing. So we're focusing on this only, just for the moment. Okay, so here we are. Let's see, arbitrarily, I'm going to pick my order to be like this. I'm going to do dy dx. In other words, I'm doing my x slicing, and then I'm going to do y slices of my x slices. As you might say, dx is on the outside. You could say you're going to do the integral dy dx, whichever way you want to say it. Okay, so what's my range of values of x? Well, there's my first x slice. There's my last x slice. I think it's a pretty easy pitch that this is from 0 to 1. If you're not persuaded, though, notice that this point that is my first slice is that point right there that has x-coordinate 0. Thus my lower bound 0. And pick any one of these points, whichever one of these points you like, doesn't matter. For our last x slice, these 2 points both have the same x-coordinate, giving me my upper bound for x of 1. All right, is everybody happy? Right. All right, so x goes from 0 to 1. Okay, now with that done, I'm going to fix a value of x. We're going to focus our attention on just that x slice. We now are going to move to the inside bounds. Let's try to figure out now what are my y bounds. I'm going to start with the easy one. I'm going to start with the lower bound. This lower bound is defined by that point. Right? So the lower bound I'm interested in, defined by that point, which is on this curve, which conveniently, very easily, has an easy equation. It's the x-axis, so the equation is y equals 0. Now here's where a lot of students go a little too quick. You wouldn't get a wrong answer if you were too quick in this case, but we're going to see some examples where you really would. So I think it's always valuable to be cautious at this stage. Don't just immediately put down 0. Think through, wait a minute, what am I doing? I'm looking for a y bound. So I need, in this equation, I need to solve for y. Good news, it's already solved for. That's awful handy. So yes, it is the case that that lower bound is 0. But again, make sure to consciously, deliberately think of it as solving for y in this equation. Because in some cases, it's going to look a little weirder. Okay. Everybody happy with that lower bound? Okay. Now let's talk about the upper bound. How are we going to find the upper bound? This upper bound comes from that point. That point's on that curve. Now we're going to have to do a little bit of work to figure out what this curve is. This is not an axis, so I don't just immediately know the equation. But notice, this curve contains 2 of our given points. And then think back to high school algebra. If I know I have a line that goes through 2 different points, and I play algebra games, you find the equation of the line, and that equation of that line is this. And now again, pause. Slow down. Don't just immediately write down. A lot of people will just, again, instinctively just, pick one side of this equation. It matters which side we pick. Remember, for the purposes of the inside integral, x is a constant. X is a constant. Remember, furthermore, let me just declutter here. Let me get rid of all that. What am I solving for here? I'm trying to find my y upper bound. Because I'm looking for my y upper bound in this equation, I need to solve for y. And I get x. Again, if you'd played it a little fast and loose, you probably would have gotten the same thing. Again, that will not always be the case. Okay. So, done. There's our iterated integral. What do you think? Questions? Is everybody happy with where this came from? And compute, of course. Okay. Here's another one. Let's see here. Same region. We're just going to slice in the other order. Here I'm going to do dx dy instead of dy dx. I'm going to move a little faster because we've got one under our belt already. What's the range of values of y? Well, y starts there at 0. Y ends here at 1. And so the outside integral is 0 to 1. Again, you can see that directly from the given points. Yeah, sometimes the fish jump in the boat. But now we're going to fix a value of y. We're going to look just at that y slice, and now we've got to think through what is the range of values of x. Starting with the lower bound. The lower bound is defined by this point, which is on that curve, which has this equation. Honestly, I'll tell you, when I do these, I find myself that after I've identified a point and drawn a line and thought about the equation, sometimes I forget, wait a minute, which variable am I trying to find a bound for? Right? So look back into your integral, see which is the variable for your inner integral that you are therefore trying to find a bound for. X, I see here, is the variable I'm trying to find a bound for. So I need to solve for X in this equation. I get this answer Y, which feels a little uncomfortable, but don't forget Y is the outer variable, so it is a constant. And so sure enough, I have found X. I have solved for X in that equation. Perfectly okay that it's got a variable there, because it's not a variable. It's a constant. Okay. All right, and then upper bound. Let's see here. Upper bound. Let's see. The upper bound is defined by that point. That point's on this line. That line has that equation. Reminder to myself, I'm solving for X. So, okay, again, already solved for. Again, sometimes it's easy. Upper bound, then 1. Yeah? Everybody happy? Kind of doesn't matter which way you go in some sense. Do notice, however, that we don't... Oh, come on, my eraser button. Here we go. Okay. My answer that I got from doing dx dy compared to the answer that I got doing dy dx, take a look at the bounds. Notice this didn't work out. Right? You can't just switch the, when you have non-rectangular domains, I hinted at this previously, these bounds and these bounds are not just trades of each other. They can't be. So, again, that only works for rectangles. If you do the slicing in the other order, you've got to completely redo your slicing process. Okay, moving along. Let's see here. We're not going to make it through this example, but I just want to start a little bit. Notice we've got this curve y equals x squared, and we've got this curve y equals 4. My domain over which I want to do an integral is the domain that is bounded by these two curves. And we have to talk about this language, bounded by. This means two things. The first thing that it means is that the boundary of our region is those two curves. The problem is that there's several regions for which the boundary is these two curves. For example, just to, just get the ball rolling, this region here that extends infinitely, to the upper right, that region, its boundary consists of, well, as stated in the question, just the green and blue curves. So is that what I'm talking about? Or possibly, maybe it's this region here. Or possibly it's this region over here. Right? How do I know which one to pick? The second part of what this means will clarify. The second part of what this means is the domain D that I'm describing here actually has to be what we call bounded. You have to be able to put a fence around it of finite length. It can't extend infinitely in any direction. You have to be able to fit it entirely inside of a box, if you want to think of it that way. And there's only one region in this picture whose boundary is those two curves, and that is not extending infinitely in some direction, and that's this right here. So it's going to be very important to interpret these questions appropriately. Part of the question is to interpret the question appropriately, and this is the region bounded by. Okay, how are we doing? Is everybody with me? We're out of time. Call it a day. Call it a week. And we will pick up here on Monday. Y'all have a great weekend. Oh, real quick. I do have the exam grading done. I just haven't had a chance to fix the curve and etc. But by the end of today, I am going to teach a class in just another, my last class in just a few minutes. So probably around 5 o'clock or so would be my guess. I should be able to have grades posted. So be on the lookout. See you later. Yeah, with the curve and everything. Yep. All right. Y'all have a good weekend.